So just to have a quick feedback, how many of you are familiar with CQRS? All right, keep your hands up. No, move. How many of you are familiar with actor model? All right, few of you. Okay, so I'm personally a performance junkie. I like to build, applications that run faster. Generally, everybody like build applications that run slow, right? So what I mean is that it turned out that CQRS can be used, if you use correctly, to build in specifically for some boundary context, right? Can increase the performance on your application. And it turned out that also the actor model can be leveraged from CQRS to all the goodies that come from the infrastructure, such as resiliencies, fault tolerance, and so forth. So this is a talk about the evolution, to me, from CQRS to a little bit better CQRS, because we're going to build CQRS using reactive programming and the actor model. So the agenda here, we're going to cover a little bit why we arrive from the old traditional way to write application to today to using the reactive manifesto and the CQRS. We talk about CQRS and a bit event sourcing. Then we're going to discuss about where functional programming fit in this context, and then of course dig in CQRS. And I like to show code in my presentation, so there's going to be plenty of code. How many of you are .NET developers here? I saw so. All right. So, but the code is in .NET. However, the main concept really can be applied regardless of the technology you're going to use. All the slides and code are on GitHub. So in the end, you're going to get the link you can download and use it. The main objective is that to do an application that is run better, you have to apply some changes, right? So the main objective, take away that sometimes you have to experiment new approaches. And of course, CQRS combined with the actor model really bring up to the next level what is this pattern of command query responsibility segregation. And of course, let's go reactive. Briefly, about me. I'm originally from Italy. However, I lived the last 10 years in the area of Washington, D.C., US. I played with a lot of different technology in my career, but I embraced the .NET in the last 8 years. And I just recently, actually a week ago, completed my book of functional concurrency in .NET, published by Manny. And I like to believe, that to find the right tool for the right job is the right way to write programs. So I want to start with a story, though. And so I been hired for a company, but for privacy, I'm not going to tell them the company, and I'm not going to tell the software that I had to build was a payroll system. Okay, so for privacy, let's say that this application is a phone. Okay, so this company have this phone they had to run. However, it turned out that they have a big chunk of the market, but after a while, a new vendor came along, more modern application came along, and they start to feel the pain, right? And the problem is that this phone wasn't be able to compete with the new phone, right? They try, to use it, make selfie, but it didn't work out quite well. So they decide to get together in a room, all the business people, and see what they can do. And they say, well, we're going to build a new application. We're going to build a new phone, better. So they start to discuss about, well, what we used last time. What kind of tools we used? Well, we use an entity framework like Hammer. I don't know. Let's get a better one, 6.0. We use a web form like a screwdriver. Let's use MVC. And, so why not for building a phone? And they get, a powerful, sounds good, a powerful saw. So it turned out that, yes, they was able to deliver a better application, but still not quite competitive, right? So what was the main problem? Well, the main problem is that they have is that the application must have some sort of requirement, such as scalability, responsiveness, and so all the nice buzzword. But they have, in mind the fact that they really didn't change the architecture model. They use the same blueprint. Yes, they changed the tools, But when you are in a meeting and to build an application, they start to talk about tool, please run away. That's not the way they want to build an application, okay? What you have to do instead is try to avoid to repeat the same action, right? Yeah, you can change tools and build a better application, but most likely it won't be a fantastic, a superb application. What you have to do is really change the blueprint, change the problem from the source, right? The architecture model. At that point, the tooling are just an implementation details, right? This can be any sort of tooling you're looking for. So in retrospective, what was the problem? To me, the problem is that sometimes you have to look out the window for new solution. It can be strange in the beginning, right? It can be weird. But, and the reason is that we like to be in our comfortable zone, right? We like to stay with what we know. We don't like to see or try something different because we don't know what can happen. At least if something goes wrong, well, we already deal with this problem. We know how to deal again. But it's true also that really we're not in control. We're a follower, right? The industry really what set the evolution, how the application has been built. Now, I don't want to bore you here, but if you think about it, we started with a two-tier application many years ago. And at that time, that was perfectly fine, right? We have a tier with database and our business logic in the same server, the same tier. And it was fine at that time. Then, of course, it got to be better. Maybe it'll be a DDD. We extract the database from different machine, more fault tolerance and so forth. Probably a lot of code repetition in my mind, but in my opinion, but it was better. At that time, it was a perfect approach. It then evolved again, to the service layer, when actually we was able to reuse service across domain, right? And really, we can be able to build this application that service can communicate across the boundaries and really benefit from this architecture model. And that's lead a little bit better even to sleep with the system, like sort of. But the problem here is that we have a load balance there in the beginning, and we can dispatch the request to different distributed systems, different part of the application, which is fine. But there is still the same problem that I carry on from the first slide to this one. And the problem is that we always the same issue, the bottleneck, the database, right? Think about you have many requests coming along to the database, and they're queued up. If you not build correctly, like asynchronously and so forth, well, most likely the request, you're going to pile it up until you reach the point that the server is going to send you back a request timeout, right? What you're going to do? You just increase the timeout in the config file, and you're done. Well, probably that's not the right approach. So next, finally, we have this system that actually decide to have a replica database for each part of the database replica for each part of your system. So now we can really build in a truly distributed system. And the problem though here is that we had another issue to solve, which is the session, right? So now if the request came along, if you had to carry the session, well, because you start from one point through the load balance and hit one part of your system, you never know if the same request is going to hit the same server, right? So now you have to take care of the session. So yes, it's great to have a replica database. You have to be careful to synchronize the database. That's another issue, but really the problem is the sessional state. Well, to me, a great solution really, try to build stateless application, right? Now there is this buzzword about a stateless server, right? And all the idea that you don't handle anymore the server, you build application that don't carry stateless, which is very functional, right? So we're here, but let's go flash forward, right? Let's run faster a little bit. So today we have these microservices, which is opinionated, but is a great architecture model. So now we're able to really separate all the domain in our application. Team can work specifically in one domain of the application. Their service can be expand or contract based upon the response, can be more responsive and fault tolerant. And so all this problem pretty much goes away, right? So why this evolution, right? Well, if you think about it, in a late 90s, we have like around 280 million users that was connected online. And then 2005, we have pretty much maybe over a billion users. At that time, 2005, Twitter, Facebook, it was really a thing, right? And you move forward, and these days, in 2016, last year, we have over 3 billion users. But what is interesting to me is this number here. Twitter by himself, last year, well, probably today even more, was able to handle by himself what was the connection in internet in the late 90s. So why this evolution? So why do we need all this change? Because scalability, right? We need to build application that are responsive, regardless, what does the request to come in your system. So it's able to cope based upon, the more workload your server receives, and the response is going to stay stable over time. So the secret sauce, I call it ACID, not drug related, but it's asynchronicity that I mentioned. But keep in mind now the definition that you can find online is an operation that complete later in time, in future. And we're going to come back later. Caching, of course, I try to avoid to repeat the same operation multiple times. And distribution, of course, when you partition the work across multiple machines or processing. So asynchronicity, it seems that you, the majority, are .NET developer. So when I ask you what is asynchronicity related to .NET, you most likely think about begin something and something else. Now we have the cool async and await. Well, the truth actually turned out that asynchronicity can be also a pattern, right? Can be an architecture model. Think about when you buy something through Amazon, right? You're not going to get your shipment right away when you click checkout or pay. You get a notification that said, okay, your order is going to be processed. You receive a notification later. What's happening is that your order is going to be queued. And some point later in the future, it's going to be processed, right? So even queuing or later process some jobs, this is also the definition of asynchronicity. And this is start to be a bit more relevant when we're going to talk about CQRS in a second, because now when we're going to push something out to be processed, it doesn't need to be processed right away, okay? It can be processed later on. All right. Now let's go back where we're at. Reactive Manifesto. How many of you are familiar with Reactive Manifesto? Okay, a few hands. So Reactive Manifesto actually is a manifesto paper that was written in, I think, 2010 or refresh 2013. And recently in 2016, main vendor company from Netflix and Google and so forth published, they say, yes, we agree to the Reactive Manifesto as the way to build reactive programs. And really what it does, Reactive Manifesto, is define the properties that your system must have to be reactive, such as responsive, which is pretty much what I talk about scalability, right? Always be able to respond back in a constant time. Resilient, which when the system is able to self-heal, right? Something go wrong, while able to react to the problem and bring back the system shape it was in the beginning. Message-driven, when you have some sort of asynchronous message passing semantic, and message passing is going to be very important later when we talk about the actor model. And elastic, this is also related to the fact that, as I mentioned earlier, the system is able to cope to be responsive, also to expand or contract, scale out to increase the resources to be more responsive based upon the request. Now, keep in mind this Reactive Manifesto, because in the end, we're going to go back here. All right, CQRS. CQRS stands for Command Query Responsibility Segregation. And really what it does is a pattern. It's a pattern that encourages you to divide the domain model from the read and the write, okay? So think about an horizontal line now from your architecture model. Instead to be layer or tiers, we're going to have like a big line go across and divide the read and the write. This is a definition that Greg Young, one of the two guys behind CQRS pattern, gives. But really, to me, if you read the CQRS, it's nothing more than common sense, right? It really a recommendation that the code that does the query is separate from the command that do some change of state. But what is the benefit, right? Well, I'm glad you asked. So the benefit is that now you can target the two different parts of your application using even different tasks. You can optimize the read and optimize the write. Team can work specifically in the read part of your domain, and team can work specifically part of the write of your domain. Okay, this is a simplistic image. I have a more pretty later. But the idea is that you really have your client that send a request, and you have one part in top that does the query. You can see there are two ways, of course, push the query and get the response back. And the write is send the command and hit and do some state of change. What is interesting here is that we have two different databases, the read and the write. And we're going to go back later. It's not mandatory you have two databases. But the idea is that if you have two databases, which is my favorite way to build it, it requires a bit more work. But the results are really worth it. Because now you optimize your database for read, and your performance can increase. Now you don't care about to have the bottleneck of one database. You can have multiple databases of read. And it just happened that the write and the read need to be synchronized. And this brings a little problem that's called eventual consistency, which is not really a big issue to me and can be overcome later. We're going to see how. And actually, we're going to talk about eventual consistency. But to complete the definition, we have the command. The commands are usually imperative, like submit an order, give me a beer. Really change the state of the application. Really, command can be rejected because you go through a pipeline of validation of your domain, right? So it doesn't really necessarily that the command actually is going to do something. It can be rejected. On the other side, we have events, which is the output, right? Which is the result. After the command is being pushed, if validation is successful, the command run, and then an event fire up to notify that something happened, which means that event can never be rejected because they run out as a consequence that is something that already be validated successfully. And the event doesn't change the state, right? It just notify. In fact, as you can see, it's past tense, like order submitted. Okay, this is a little bit better image of CQRS. We have the client that send a request to the read and send back, the response. And completely on the side, you see this is the boundary that divide the read domain part of your application to the write. Then you have the write that send the command. This is a command handler that actually receive the command and handle the command, maybe some validation, and publish the command to its subscribed. And then do some change of state, maybe write to the base, persist in somewhere. And as I mentioned, then we have the event that is raised. Now, it's not necessary that the event is persistent. You put just the persistent in the same database for simplicity, but can you do anything else, right? And actually, these arrows are supposed to be database. As I mentioned here, when you use two databases, that actually is give you more performance improvement, you run a problem that is called eventual consistency. Because what's happened is that when you do a command, not necessarily the read part of the domain is going to be updated right away. So it might be that the user will have some stale data, right? But when you query or you make a search in your favorite search engine, most likely what you get your data, the time you receive it, already stale, right? So really, the eventual consistency become a small problem to me, and usually it's the SLA, the business people, that tell you, what could be the gap or how often should be synchronized the two database. Can be a few milliseconds, be second, can be minutes, hours. We don't know. But the idea really separate and synchronize. However, we're going to see how we can overcome this using the actor model. So the benefit, quickly, there are a bunch, but really, what I like the most at this tool, right? Almost infinite scalability. I don't make this up. This is like, part of the CQRS paper. And also the fact that increase the performance, no doubt. Especially CQRS is not silver bullet, but there are some specific boundary context in your application that can definitely leverage this pattern. So that's a CQRS. We have a command. If you think about command, you push something out. So let's talk about how command can be interpreted. Let's talk about actor model. I didn't think about a red slide and a big screen, right? Hopefully nobody can see it here. But the actor model, really, I'm going to go forward, is this small unit computation that is independent, isolated, and communicate only through message passing, okay? Which is a great concurrent programming model. Because now, because isolated, there is no share of state, which is the main problem when you write concurrent application, right? So the actor model is composed through few parts. You have the mailbox when you send the messages, and the messages are queued up. The trick is that the actor model actually inside is just single-threaded, right? It's nothing super fancy, but it's the isolation that really the secret weapon here. And when it processes one message, all the other messages coming in are buffered, so they're not lost. And all the messages that you send are sent asynchronously, so no blocking, which is great. Any questions so far? Okay. One other great feature that the actor model brings to the table that can be leveraged in CQRS is all the infrastructure that came along. The one that I really think is very helpful is the supervision, which means that the actor system is able to embrace the let it crash approach, okay? What does it mean is that, think about like a rental car. You drive a rental car and you break the car. Well, you don't care about to fix the car, right? You call the rental company and send you a new actor, right? You send you a new car. So really embrace the let it crash approach. And that's what really out the box you'll be able to build fault tolerant and resilient system. So really what the actor offer, is high throughput, as I mentioned, asynchronicity because the message passing semantic, fault tolerance, and also the scale out and scale up. This is pretty cool. They use something called location transparency. Without going too much in detail, high-level idea is that actor can communicate with other actor, and they don't know where the other actor are located, right? They can send a message, and the actor system is going to take care to deliver the message. So which means that the actor can be in another system, same machine, across the process, and so forth. So really, same API to scale out and scale up, which is pretty cool. And I really think that the combination of the two models, the actor model and CQRS pattern, really, to me, are just meant to work together. We have CQRS that can be helped by the actor model because the resiliency built in as infrastructure, the asynchronicity built in. So when you send a command through CQRS, you definitely want to implement asynchronously, right? No blocking. And actor model just do it for you out of the box. Now, interesting, if you think about a few definitions here, we have a message-driven the actor, right? Because it's passed to message passing, which is also related to the command dispatcher or the command handler in CQRS. Then we have the responsiveness, right? Because the actor model is asynchronous, and CQRS is really built in with the idea to make your system more responsive. Elastic, well, because you can group the command handler in different actor and then expand in your system in multiple actors to be more responsive and elastic. And of course, it's asynchronous friendly, which brings us to the pretty much reactive compliance, right? So definitely CQRS and actor model really give you a great opportunity to build reactive application. All right, so this is a little bit different architecture, right? Because now we have the message bus in top, which is our actor system, actor model. You send the messages, and now you hit the read side and the write side of the application of the CQRS application. Now, what is interesting here are the two aspects. One, for each box, right, now you can have other actors that handle the command per se, concurrently, and asynchronously. But also the bottom. Now, we have the issue about eventual consistency to keep database synchronized, right? But what if I tell you that now the actor received the message and it can maintain some state and actually using the persistent actor, which might keep in not just in memory, but persist your information persistent your information. Well, now you have the actor that is able to respond immediately if some data change, and then underneath it asynchronously coordinate and synchronize database. So right now you overcome the limitation of eventual consistency using the actor model. Event sourcing. So I want to talk just 2 slides about event sourcing. Usually event sourcing and CQRS, they go hand by hand. They are actually quite nice to be implemented together. They're not mandatory to be implemented together, but it's easier to implement event sourcing with CQRS. And think about event sourcing easily as an event journal of your application. Whenever happen, you keep a state, but in a mutable manner, which means that the event that happen are always appended, okay? And what does it mean as appended? Well, think about shopping cart, right? Shopping cart, you put item that you want to buy, you remove item, and then you check out. All this history, it keeps track for you. Like for instance, you search for a product 1, you add the product to the cart. Well, you change your mind, you want a product 2, so you add the product 2 in the cart, and you remove the product, right? You keep the journal, you keep the history in the journal or your events. All right, so let's bring a bit to Reactive extension. And how many are you familiar with the Reactive extension? Okay, Reactive extension is, well, there is something called observer pattern. It was so important that Microsoft decided to introduce part of the core framework in 4.0. And Reactive extension really simplified the implementation of the observer pattern. It's based on 2 interfaces, which is observer pattern, which is implement 3 methods, on complete, on arrow, and on next, and the observable, which just complete the subscribed. You just create class object that implement the observer pattern, you're able to subscribe to the observable and send notification, and all the observer receive a message. If you back here, the middle one, the subject, is just the implementation on the 2, which is quite nice and convenient. If you create a subject object, they're pretty much able to register any observer that you want and communicate and send notification using the same API as it was an observer. The main idea really the conversion of from pulling to pushing, like from the enumerable, when you, for instance, you have a for each, you ask for some more data, you ask for some more data, but there is no more data, you kind of block, right? Instead, Reactive or the observable pattern is pushing, is give you more data until there are, and then doesn't block, and then send you data when they arrive. So asynchronously, no blocking. It really is a way to manage asynchronously event. And what is nice, they provide all the nice link semantics. So familiar with link, you have all these high order function you can apply against event. It really bring up to the idea, especially with the subject type, is a little bus, right? You have a subscriber, and then you send a message and notify all the, you publish all the message notification to all the observer that are subscribed. So how we can, so far we saw a bit about CQRS pattern, the actor model, and the observer pattern, which for simplicity we're going to use Reactive extension to implement. So how we're going to use these in our architecture, right? So let's talk about the demo, and then we're going to check the code. So the application is actually, let's run it first. I think is running. So okay. So this is actually is a iOS, iPad application built with Xamarin, and the server is running on my Mac machine using the great Ionide plugin of F#. And I run it from my Windows Visual Studio, Windows virtual machine running Visual Studio. So the idea, we have a stock market. I open up, all my stocks start to update, which now the server is pushing the notification and update real time my board here. What actually is a bit cooler here is that your right side, when I have the option to buy or sell order asynchronously, which means I can put in a queue some order, and later on when when the price receive the value that I set, the order going to go through, right? So let's see how does it work. For instance, I want to buy some Apple stock. And let's say I want to buy for, let's go low, like 92.98. It seems that it's going to go back and up. So let's go 4. I'm going to go buy. You see, going to update the buy order there. Now, okay, now it pushed to the portfolio. What's happened there is that I push in my queue, and it was waiting to receive the value, the price, to purchase my stock, right? When the value reached, purchase my stock, and now my portfolio is updated. I have 628 cash, but now I have 4 Apple stock that I bought at that value, which is pretty nice, right? Well, now, let's say I want to sell it, right? I'm greedy. So now I want to sell it for more money. So let's go to 93.10. Why not? Let's sell. So now the message is said, okay, I already make 72 cents. Think about it. You put all your order overnight, you wake up rich. Come on, it's pretty nice. So what's happened here from the, let's go back here, the architecture model, we have a front end, which is our web API. And in purple is how I use the actors and Reactive Tension to be observable as well. So what's happened here is that I receive the command, I go through some validation, and the command go to the stock ticker, and then the trading supervisor. The trading supervisor is just an actor that register and subscribe observable, actually observer actor, that are this trading agent. Every time a new user connect to the application, a connection spawn up and a user log in, and then a new trading agent is created. So for each user, it creates one independent actor, with each independent state, which is contained in my portfolio, my stock order to buy, and so forth. Whenever the stock market keep updating the prices, well, the trading agent received the update. And every time check, well, I have a Microsoft stock updated. Do you have a sell or buy order? Yes or no? If yes, let's check the price. Does it match? Yes. Moving on. That's great. An update. Now, the great part here is that all these components are decoupled, built with the actor model, and each actor implemented using the observable and observer pattern. So they really use a subscription kind of model to send messages synchronously. And what is cool here is that from the CQRS standpoint, I don't have to ask the data to be updated. I don't have to ask when my portfolio submit an order successfully, because I use CQRS. So at this point, SignalR. SignalR is a bidirectional WebSocket from Microsoft that allow me to communicate between the client and the server. So at this point, when I open the connection, I'm going to keep a reference for each client to each actor. And when the order goes through, it's going to send a communication to the MyUI. It's all auto-updated. All right, so let's talk about code. All right, so let's go a bit bigger. Okay. Everybody can see code bigger, probably in the back, right? Okay. About now, is it good? All right. So this is a API controller, which everybody familiar with API controller, .NET, SP, Web API? Perfect. The first thing that is a little bit strange here is this interface, right? What's happening here is that the API controller actually becoming observable, okay? What does it mean with that is that now I can create a subject type, which is part of the Reactive Tension framework, and leverage the subject to implement my API as an observable. Why you want to do that? Well, let's check first one action, then we want to bubble up and see what's going on. There are two main actions here, which is the post-sell and post-buy. They pretty much do the same thing beside the type of sell, right? I mean, the type of trading can be sell or buy. The process request, which is this method here, it just converts my my data to the trading record, which is my message type that I want to send to submit to my spatial trading agent that keep my state. I run some validation, which I'm going to check in a second, and publish this command. Now, the command is published using this method here. So what's happened is that it checks if the validation went through successfully, it push out using on next. If you're not familiar, on next is one of the API from the observer interface. So now really my web API controller it really doesn't care where send the message, just push out the command whenever is subscribed to him, which is pretty cool because now it's completely decoupled, right? The command wrapper, I'm not going into detail here about it's implemented, but it really enriched the command with some extra metadata, such as timestamp and the user ID. So later on, if you want to run some sort of replay or event sourcing, you have a special ID as an identifier, so you can grab all the specific event to replay in the future. So I recommend you always want to have some sort of wrapper, an envelope on your command. So then you publish as an observable. And here in the bottom here, you see this implementation of the observable interface, just the subscribe method that received the observer. So this is where this is happening. Well, a startup, when your application starts, do some configuration here. Okay, you can see, activate signal R, but this is really the piece of code that use the controller activator, which is part of the Web API framework, to replace how the controller can be instantiated and sent back to the response, to the caller. So the controller activator here is implement the HTTP controller activator interface. As a constructor, interesting, get an observer. We're going to go back here in 1 second. But what it does is say, okay, I inject my own logic. I check it if a controller type request it matches the trading controller. Well, I'm going to create an instance. And because I know this is an observable, I'm going to register the observer that you pass in the constructor here of my control activator. And I register. And I return it part of my response pipeline. Okay? Now, if you go back here 1 second, at the startup, the observer pass as a constructor, I use just the observer create, which is a built-in functionality in Lattice Tension, to create an inline observer. And you can see here what I do is say, for whenever the controller call on next, pass the on next and send the command to the agent post. The agent post here, you're going to go up here, is just create an instance of the action block, which is part of the TPL data flow. TPL data flow in the .NET, if you're not familiar, actually is a great technology. It really provides a set of building blocks that you can build in some sort of pipeline in mind, right? But the great thing is that they communicate to messages like an actor, and they're all asynchronous, right? So I create this instance, and whenever I send and post the command here, well, the action block in this case is going to handle the command and do some magic. So when they send the command to the handler, okay, which is our command handler. So how this is implemented? But remember, at this point, the command is sent out asynchronously. My web API request is gone, is done. Already received the response, it was better request, it was okay. If it's okay, my command is keep going. Being validated, if it was validated, it's gonna go through the pipeline here. So my client is done. So the handle here is built in a command handler. This is a F#. Anybody familiar with F#? All right, few. Cool. Well, I think it's pretty easy to understand. Just remove the curly bracelet and put a let inside the var, and pretty similar. But the idea is that I have this function, the handle, which is the one called from my TPL data flow action block, call the async function up here, passing my command, and run as a task, which is API here to run the task immediately. The async handle here, it just kept the envelope by command and send the command and publish now to a different place of the application, which is my trading coordinator, which is built here, right? It's funny how I always like coordinator manager name, I don't know why. But so I send the trading coordinator, we're gonna go there in a second. The following, I'm gonna create an event based upon my command type. So I use a pattern matching here, okay? So I check if it's command type, which is a trading command. If you hover the mouse, if you can see it, but trust me, it's a trading command. Check is a buy stock command or sell stock command, and you create the related event, which is stock buy, which is past tense, right? I create this event, and then I send and store it to the local storage event. Now, for simplicity, this is just in-memory implementation, and use a dev built-in mailbox processor, which is just a local in-memory actor agent model, similar to the actor, which is asynchronously wait to receive a message, which is this line here, and when receive the message, it applies some functionality. In this case, pattern matching against the message received is if a save event, notify the event to who is registered using the event bus notify here, and in this case, I persist the event in memory using dictionary, but just for simplicity, but this can be your database or whenever. In the event notify here, it's just simple using Reactive Tension to just subscribe and publish event to notify when something happened. The retry publish here is just in F# computation expression, but just asynchronously retry if something goes wrong a few times, right, with some sort of delay. The instance is created above here. It said try 10 times, 250 millisecond delay if something goes wrong. The implementation, without too much detail, is up here, but you can download the code and take a look for more detail. So let's check actually two things that will be interesting here. The trading coordinator, which is up here. So the trading coordinator is this class, this object. Type in F# is used when you create like a class in C#, okay? So this is a class trading coordinator. I use a Lattice Tension, pub and sub, which underline actually just use the subject type. So it really extract the subject type and create in top publisher and subscriber kind of pattern. So nothing fancy. You can use even subject here from the Lattice Tension. But what is cool here is that now the F# mailbox processor, the agent, is it become like a hub, right? It become the observable where when a connection happen, the user that become an agent, right? There is one agent for each user that is connected, is subscribed to this agent. It really, what it does here, when receive a notification, it dispatches the command to that specific agent based upon the unique identifier, or dispatch all the update of the prices when the stock market send a notification that something happened. It is all done asynchronous, no blocking, and concurrently. I'm going to just check one of the messages type, but it can be subscribed, unsubscribed, and publish command, right? So the subscribe, you can imagine, receive a notification when the user start the first connection through Signal Hub. When receive this connection, it creates a trading agent, which is an agent, but is an agent that we're going to see the next piece of code is an observer, right? So now you can use the agent using the API such as onNext, onComplete, and onError, okay? So I subscribe the agent, in fact, using Lattice Tension. So now my agent become an observer, which is pretty cool, because now all the commands are dispatched using the observer pattern. I'm a diligent, I do some sort of supervision, which in this case, this is a helper function that what really does is say something goes wrong, notify a parent, which is my supervisor agent here. Nothing fancy, just do some logging. But more sophisticated approach to be probably do something else, like spawn a new trading agent, notify in a better channel, and so forth. And when it's done, I pass the instance to my local state here, which is recursively passed, which is immutable, right? Recursively passed to the next iteration, waiting again for the next asynchronous message coming in here. The map type in F# is like the dictionary equivalent in .NET, but is immutable. So you never modify an existing one, you create a new one. And the publish command is really when you push the command, is there some order to buy or sell to the trading agent that are listening, right? So they're observer in this case. So in this case, you can see here that I receive a sell stock command. I check the observer, which is my trading agent, if it exists. If it exists, I'm going to pass the command using what? The onNext API, which is a reactive extension. But the reality is that the command is passed asynchronously because use the underlying agent, right? Message passing, which is pretty cool. And the implementation of the trading agent is very simple. This is pretty much a trading agent, again, using the Mailbox Processor in F#, which is great. This is an instance for each user connected, okay? So you can see here I have my local state, which is my portfolio. And then I have the threads, sorry, right? The threads, which is one for sell and one for buy. Whenever I push a command to buy some stock or sell, this is going to be updated. And down here, when the stock market sends me a notification here to update the price, it's going to check with some functionality. It's going to check first if there are any sale. If there are any sale, it produce and submit the sale. And you want to do the sale first to make more money. So probably you have more money to buy if there is an order next, right? Then you buy, and then here you access the local instance of the signaler, which is passed in a constructor when you create the trading agent. If you over the mouse, you see the type here is small, but is a high-hub caller connection context, which is part of the signaler connection. Now, my UI, my client is updated, and my order is updated here in a local state. The cool part, this line here. This is how you implement an interface in F#. You just said, I implement the interface observer, and this is my functionality. As you can see here, I implement the onNext and onComplete API of the observer interface, but the reality is that what I do is I send the command to the agent, right? All right, the last part I want to show here is simply the stock ticker, which is the signaler hub, which is now running on my Mac machine here. And that's how you implement the signaler, which is the hub. And whenever you connect, you send the command to the training coordinator. All right, so that's pretty much what I have about the code here. You have any question? I know I'm going to be late. I start late for problem, but do you have any question about this code? Let's see if it's running. Of course, it's waiting. But anyways, any question? So I'm gonna here is the architecture model, just to give you a refresh. But if you have any question, I think we are already over time, right? All right. So I hope you enjoy it. Kind of interesting how you build CQRS using actor model reactive programming. And Tomorrow, I'm going to talk about ACA streams, another interesting topic. Will be different. There will be some 3-slide overlap about the actor model. That's it. Otherwise, all the topic will be different. All right. Hopefully, I'm going to see you tomorrow to the next talk.